Yeah, issues with steady state analysis. What we're trying to find what a particular measure is. We've been focusing on the means, that is the true but unknown expected measure. It's not the only one. We might be interested in the variance. We might be interested in, say, the maximum or even the minimum. We might be interested in a quantile or the median. All of these are potential measures. The most common are means, expected values, and understand that that's still not the be all and end all. It's just one of the most common ones. And oftentimes when a measure is discussed, it won't be explicitly stated that it's the mean. So for example, one measure that the Navy is particularly interested in when it comes to certain inventory things is something called fill rate. And that's the term that they use. What they really are getting, or what they really mean, is the expected fill rate. Namely, basically, say, like for a replacement part on an item, when they go and try to get it from Mechanicsburg, then what is the probability that they will be able to actually get it? Or will they say, okay, we can't give it to you now, but we have to order, buy it, order it, repair it, whatever. So fill rate is something that they're very interested in. And in the models, the fill rate is done by having some kind of model which simulates these demands, and then just says you get a 1 if you could satisfy the demand immediately out of stock, and you get a 0 if you can't. And so the fill rate measure is actually the expected value of those 1s and 0s that come up. And in a model like that, what they are interested in the steady state value of that. In other words, if I start with a whole pile of them, then, so if I have 100 of these items in stock, then the first 100 demands that I get for it are going to be satisfied immediately. So I'm going to have a fill rate of 1, and that's great. The problem comes in is, well, given policies for replenishing these items, what's the fill rate going to look like after a while? And that's a different matter, and that's where this kind of steady state analysis comes into play. So the issues, which are very important, have to do with, well, first of all, initialization bias. In other words, the simulation starts off in a particular state. And this, in our canonical example, this is their multiple server queue. It starts off empty and idle. And as we can see in the values, if you kind of squint a little bit, you can see that, maybe I can make this a little bigger here. You can see that the first 2 guys always have a 0 delay in queue. That was because for this particular model, there were 2 servers. And so if the system starts, with no customers in them, and then the first 2 guys in are always going to be able to get immediately into service. But as you can see, the third guy sometimes gets immediately into service, and then sometimes doesn't, sometimes has to wait a little bit. But that wait is actually, on average, pretty small. And as you go to successive customers, you can see that the expected delays keep increasing. We can kind of see this here. So it starts really small. But what does steady state look like for this? Steady state doesn't look like what these values are down here. Steady state looks like more what the values are up here. And so the solution, or a solution to initialization bias, is like the old joke. It hurts when you go like that, don't go like that. These observations hurt. They hurt your attempt to estimate this steady state value here. In other words, if I'm trying to estimate, if I'm taking observations from a distribution whose mean is 35, mean is around 35, if I include in that observations from a population whose mean is considerably different from that, as it is down here, that is going to strongly bias my attempt to get a good estimate on what this value is. In other words, and look at this. It takes at least 6,000, by 6,000 customers, we're starting to get fairly close. And we only start kind of fluctuate in this particular case. We really, it's really some, maybe around 7,000 that we start to get observations that are arguably in steady state. So basically what we have to do is we have to, well, remove these observations because they don't work for us. The second issue is autocorrelation. Again, this is what we looked at last time from a single replication of this for 100,000 customers. And what we're looking at is the autocorrelation, that is the correlation between successive delays in the queue. And we see that that correlation is extremely high. In other words, what that means is that if you observe one customer's delay in the queue, then the chances are that the next customer's delay in queue is going to be very, very similar to what that is. Just informally, that's what this high correlation means. And we saw that if we extended that out to 200, a lag of 200, that is the customer, if I look at delays in queue for customers that are separated by 200 customers, the correlation is like 0.87. Again, that's very, very high. That's way far away from independence. That's something to be concerned about. So how do we deal with that? Well, it's something called the replication deletion method is the most straightforward brute force way of dealing with it. Okay, so what is the problem now? So our measure in steady state is just one number. So describing what we're trying to estimate is much simpler than in the terminating case. In the terminating case, we were getting observations that were not identically distributed. And in fact, this is a demonstration of that. In other words, if in our transient, let's say in our transient analysis, we're only looking at this piece right here, say maybe the first 2,000 customers or so. Well, as you can see, this is a rough estimate of the true mean. Again, it's an estimate, but it's an estimate with like a lot of replications. So this is actually fairly close. But each one of these has a different mean. In fact, you can see that in the numbers. And so if I have a sample, remember the basis for a quote random sample from your statistics class was that they be independent and identically distributed. And for these kind of data, we're 0 for 2. They're not independent and they're not identically distributed. So for the terminating case, though, you have to do a little bit of a dance about what it is that you're estimating. If I'm taking the average of values that aren't identically distributed. So there we have to say something to the effect of, this is the expected average delay in queue of our customers over, say, the first 10 hours or however that's defined. So describing the measure is challenging in the terminating case, but estimating it is easy. You just kind of run the simulation for that certain amount of time, allowing the initial conditions to affect the result, and then just perform independent replications. So that's a piece of cake, well, relatively. In steady state, we can describe, this is just one number now, so that we can describe it easily, but we have these two big challenges, namely, we can get it, like assuming that we can get to steady state. So let's say, all right, we truncate at a certain point, and we say after this point, we're gonna just kind of keep sampling. So we've removed the initialization bias, no problem. But we still have the problem that the even in steady state, they're actually identically distributed, but they're not independent. They're not independent. And that creates a problem when we're trying to estimate our confidence interval, because that requires estimating the variance. And to estimate the variance, we require independent observations. Now, there are kind of some fancy ways of trying, time series analysis ways of trying to estimate variances when they're correlated, but that's a little bit beyond the scope of what we're talking about here. Just using standard statistics, we have to deal with the fact that we have correlated data. We need to estimate the variance. We need to find some way of making them independent. And so, oops, we have this replication deletion method. So, and that consists of two parts, which we do backwards. So it really should be called the deletion replication method, but that doesn't have the same ring for some reason. Okay, so the deletion is that we warm up our simulation up to some truncation point. Where do we get that truncation point? For our purposes here in this introductory class, we're punting on that. We're just saying, okay, we're gonna maybe look at kind of look at this and just kind of eyeball it. And again, there are some fancier ways of doing that. That's a little beyond the scope of what we're talking about here. Just be aware that there are fancier ways of doing that. But just based upon eyeballing this, we can kind of see that maybe around 7,000 or 8,000 of these delays, it starts to settle down. Okay, so that's where we get the truncation point. And what we do is we actually delete all the observations up to that point. In other words, we, from our statistics objects, remember our statistics objects have been sort of collecting all this stuff. What we want to do is when you reach the truncation point, we're going to just remove all those. And then we're going to keep collecting more observations, assuming that it is in steady state. Again, how can we make this assumption? If we have chosen our truncation point well, then we are reasonably in steady state. Theoretically, you never actually get there, theoretically. But from an engineering standpoint, we get there for all practical purposes. Okay, so that's the problem of reaching steady state. And it all comes down to finding this truncation point, which again, we can do by kind of eyeballing things the way we've done here. And for many purposes, that's good enough. But then we need to form a confidence interval. And I hope you come away understanding the importance of a confidence interval, because even if you kind of go back to the sequence of why we need to do this kind of analysis in the first place, because these models are stochastic, one replication is just not going to do it. And what I want you to sort of keep in mind for something like this is the idea of flipping a coin once and trying to estimate the probability of heads. I mean, it just doesn't make any sense. If we perform multiple replications, we can estimate the mean, but we still, and that's better than just doing it once. But we still have the problem of, have we replicated it enough? In other words, how close is our estimate of the mean to this true but unknown value that we're trying to determine? And so that's why a confidence interval is important. And that's why we need to do replications, independent replications, so that we can estimate the variance, which in turn allow us to create the confidence interval. So we do all this, that is, we warm it up, we delete all the observations before the truncation point, then we collect a whole bunch more and get that, and that's one. That's one replication. And then we do it from multiple replications, and if we are careful about just not, if we just leave our hands off the random number generators, then they are going to be independent and identically distributed. Why? Because we are performing the same experiment under the same conditions, but with different random variables. And now we can estimate the variance and therefore create the confidence interval. Okay, so let's see. Okay, so here's how we can do this for a tally. What I'm gonna do is I have one for a tally measure, the delay in Q, our standard one, and then I'm gonna do it again for a time varying one, just because we've been focusing on delay in Q, which is a tally measure, doesn't mean that we can't do it for time varying measures. You need to be able to do it for both. So for example, in the fill rate is basically a tally measure, because that's based upon successive demands and whether a demand is going to be fulfilled or not. But other measures, such as, for example, like what is the expected amount of inventory we have in stock? See, that's another important measure. So, just sort of think of inventory type of thing. Just maybe focus on one item. If we want to have a large fill rate, we need to keep a whole bunch of these in stock. So the more we keep in stock, the better our fill rate is going to be. But on the other hand, the more money we're going to have to spend on keeping these items in stock. And so if we have an item which has a relatively low demand, then we just have a bunch of these things just sitting around. And there are two reasons why we don't want too much of that. One is because if it's an item that can degrade, if an item that has a certain shelf life, and if I have too much, then I'm going to have to be throwing some out because they go bad. Even for something that doesn't go bad, I may have a lot of money invested in keeping these items in stock when I don't necessarily need to. And particularly in the current climate, say, well, the Navy doesn't have to worry about that because we got plenty of money. Well, they do. They do worry about it, and there's never enough. So while for these, they're also concerned about fill rate, because ultimately they want readiness and operational availability and other kind of less monetary like things. There's always money involved. So the point is that it's important to be able to estimate both of these. In other words, if we estimate both fill rate and look at the expected amount of inventory that we have on hand, that's going to be a time varying measure. Okay, so let's do the tally one first. And again, if you do a pull on the class code, then these will be in the MV3302 output directory, which is where folder, which is our package. Okay, which is where we've been putting the stuff lately. Okay, so So we're going to set the number of replications. So here I'm going to do 100 replications. Okay, why 100? Well, why not? Okay, now here I've identified a truncation point of 10,000. Where was that based on? It was based on sort of you kind of looking at something like this. And by 10,000, I felt that it was in steady state for a while. So that was that's where that came from. And then I'm going to do 100,000 more after that. And again, even though I'm taking 100,000, that's because the more you take, even with correlated, you're going to get a lower variance there. So I just want to just make sure I take, in principle, I only need to take one once I'm sure I'm in steady state, but that's kind of wasteful. That is, having spent 10,000 customers to reach steady state, I want to sort of sit there for a while. And tomorrow we're going to just unpack that a little bit. But for right now, this is what we're going to do. Okay, and we're doing the same model, this plain old multiple server queue model using our entity server, the same parameters that we were using previously. Okay, but now we don't have to worry too much about doing a lot of this by hand, because a lot of it is handled for us by what's in SimKit. There's a series of stats that have the word truncating in front of them. So there is a truncating simple stats tally. And for that, like our regular simple stats tally, we give it the name of a state, and that's going to match, that has to match the property change that gets fired from what it's listening to. But then on top of that, we give it a truncation point, or that this is just an integer that says what this simple stats tally is going to do. It's going to keep collecting these delays in queue. And then when it hits the truncation point, it's just going to reset. And that's going to be our inner delay in queue stat. Okay, remember, for these, we have an inner one, which is going to collect the data for one replication. And then we have an outer stat. So regardless of what the inner stat is, the outer stat is always just a plain old simple stats tally. Why? Because each replication now is going to produce one number, and the replications are discrete. You're going to replication 1, 2, 3, etc. So that's always going to be a tally. Okay, so how many of these do we want? Remember that delay in queue gets, the state transition for that is when a start service occurs. And how many of these are we going to collect? Well, we have the ones in the truncation point that we're going to throw away. And then we have the number in steady state that are going to, that are how many. So this is how many we need. And again, we're going to stop on this event, because that once we have this many, in this case, 110,000 delays in queue, that's going to be triggered by 110,000 start service events. Okay, now here I've run this, and it took about 38 seconds, which isn't that bad. Okay, so now when we're running longer things like this, it's kind of important to, first of all, make sure that our simulation objects have the right values. And then notice before I do the run, I'm going to say, okay, here's what I'm about to do. I'm going to do 10,000 delays with 100,000 in steady state and 100 replications. Why? Because for 38 seconds, I'm not going to see anything. Okay, then finally, when everything is done here, and this is all similar to what we've had before, here I'm going to specify an alpha of 0.01. So I want a 99% confidence interval. Why? Because I want to be really confident. The quantile is going to be, again, based on 1 minus a half alpha, and the there's going to be 1 fewer degrees of freedom. And so now I can compute the half width, which is the standard deviation times the quantile divided by the square root of n. And so when I'm done, okay, so here's our delay in Q, it's about 35 something plus or minus 2.6. So again, what is the, what this says is that I am 99% confident that the true but unknown steady state mean is somewhere between about 33 and 38. Or 2.6 to 32 point something. So again, even with all this, there's still a bunch of wiggle room here. Why? Because these, sometimes you have measures that are very, very highly variable. And that's what's happening for our delay in Q. Okay, so that's delay, that's a tally for delay in Q. Now I'm going to do the same thing for a time varying, and that's in the steady state confidence interval time varying. Okay, so it's very similar, but slightly different. So we'll see how again, here's number of replications, same number of replications, but now our truncation point is going to be a time. See, for a time varying measure like number in Q, my truncation point is a time, not a count. And likewise, the amount of time I'm going to spend in steady state is likewise a time. So, just from laziness, I chose the same time as a truncation point. Again, that's ideally what I should have done is create a graph similar to this, but for the delays in Q, not for the number in Q. I mean. But regardless, so I'm going to run it for 10,000 time units now, not for 10,000 delays or anything like that, 10,000 time units. And then I'm going to discard the number in Q data that I've collected up to then. I'm going to run it for 100,000 more time units. And that's going to be my experimental parameters. So now remember, for the entity server, the state variable Q was a set. And so to do that, I need remember we had a collection size time varying, and now there's a truncating collection size time varying. So that's a collection size time varying stat that will run until this truncation point and then clear out and then keep collecting. Again, the outer stat is always a tally. And then for this, I'm printing out here's what I'm going to do. Here's where I do it. And again, for the, I didn't point this out in the last one, but I wrap everything in a for loop and I reset, and then I reset the inner stat. And then when I finish the simulation, I take the mean of the inner stat and I pass it to the outer stat. Then forming the confidence interval, I do it in exactly the same way. Here I specify my alpha, I get my quantile, I compute my half width, and then my confidence interval is the mean plus or minus the half width. So it grinds and whirs for a little bit. But the point here is that, just because we've been focusing on delay in Q, which is a tally, doesn't mean that we can only do tallies. So we've seen any measure which is a tally, we've seen how to do it. Now we're seeing any measure which is a time varying, we can also do the same thing. And we see that a 99% confidence interval for the steady state average number in Q is 22 point something, again, plus or minus 2.5 customers. And keep in mind what the units are. Previously, if the units were, say, minutes, then it would be plus or minus 2 something minutes. Here, the number in the queue are customers. So this says that we're about 22 and change, well, almost 23, plus or minus 2.5 customers. Now, actually, we also have an opportunity to sort of do a little check on Little's formula here. So here's how that would go. What we can do is, well, we could have collected the average arrival rate from that, but actually we can get the exact arrival rate from our inter-arrival time generator, which was uniform 0.9 to 2.2. So the average time between customers would be, for a uniform distribution, is the average of the min and the max. So that would be, no, I need my calculator to do this. So that would be like 0.9 plus 2.2 divided by 2. Okay, so the average time between customers is 1.55. And so the average, the actual, no kidding, average arrival rate is 1 over that. And now if I multiply that by my average number in Q, then, oops. What happened? Okay, so I have that. Remember that the average, if I divide by, or in this case, I need to multiply it by that. So it's like 1 over that is the arrival rate, then 1 over that is the 1 over lambda. So if I multiply that by 1.55, then I get about 35 something. So so if I were to do this analysis using, say, the simple server, instead of the entities, see, for the entity server, I could directly estimate the average delay in queue. But if I didn't have that, if I only had my simple server, for which I can only estimate the average number in the queue, then I would have been able to at least come up with something very comparable. Okay, so any questions about any of this? Okay, one more thing, and then we're gonna end early today. And that is this. Here's the issue. Even for what we've done so far, how do we know if we have performed enough replication? So remember, I chose 100 replications, and even with that, the plus or minus was like 2, say 2 customers or 2 minutes, depending on which one it was. What if that confidence interval is too big? See, if you choose an alpha, see, what are the things that go into the size of the confidence interval? Remember, the formula was, well, wait, it wasn't, let me be more exact here, come on. It was S over root n times our t, this is our half width, of a t of 1 minus alpha over 2. and n minus 1. Okay, so this is our half width. So what is it that dictates the size of this? Well, our estimate of our standard deviation, okay, that's whatever it is. And for independent observations, this is consistent in the sense that as we take more and more observations, this is going to get closer and closer to the true but unknown sigma. So that's going to be more or less a constant if we take a whole bunch. But the two values that dictate pretty much how this is going to be are n and alpha. Once I choose n and alpha and perform that many experiments, then I'm stuck with whatever half width I have. So what if instead of saying, okay, I want to take this many samples and have this confidence, what if I wanted to say, okay, I still want this confidence, but I want to make sure that my estimate of the mean, remember my estimate of the mean is going to be X bar, whatever that is, the sample average. I want that much confidence that this estimate is going to be within a certain amount of the true but unknown mean here. What if I want that? Well, in that case, what it boils down to is I want a confidence interval of a given size. In other words, I want a tighter confidence interval. So how can I do that? Well, with a fixed sample size, if I say if I still want to have this amount of confidence, so if I still want 99% confidence, say, or even 95, whatever it is, I cannot achieve this with a fixed sample size. So basically what I need is I need to say, well, it boils down to it. Actually, there's a lot of math that goes into this that we don't have to worry about. But it boils down to something called a sequential method. Now, what's different about the sequential method is I don't know what my sample size is going to be. And so the method is I'm going to keep performing replications until my half width is small enough. And then there's like a little technical thing where sometimes just by chance, like if after like maybe 5 or 10 replications per, sometimes the half width is just by chance gets small too early. Okay, so I hope you see what the issue is. And so the solution to that is to have a sequential method. So let's see what that looks like. So here, what I'm saying, okay, this is the same model as I had before for delay and Q. So remember our half width was 2.8 something. And supposing I'm saying that's not good enough, I want it to be 2. Okay, so I'm saying instead of saying this many replications, I want to say this is how much, this is what I want my half width to be. Okay, same model everywhere. Again, truncating simple stats tally, everything the same there. But now, instead of a for loop, I have a do while loop. Okay, so let's take a look at this. First, I'm going to start with my initial half width is going to be positive infinity. That's as bad as it can get. So, and what's going to happen is with each replication, my half width is going to be too big, too big, too big. and then at some point it's going to be just right. Okay, so now, again, instead of a for loop, I have a do while loop. So let's take a look at inside. I do everything the same, except now I need to compute a new quantile each time because my my degrees of freedom are changing. Oh, geez. What the heck happened? Are you still there?
Yes.
I just got a message. It just said I was. Oops. Sorry, I can't tell. Is everybody still there? I can't even see you. Right there.
Yes, sir, we're still here.
Okay.
Yeah, we're here.
I just got weird messages from Zoom about logging me out or something. Okay, where are we? Okay, so so everything here is the same as before. We reset our event list. We reset our interstat. We run the simulation, and then we get our new observation. Okay, but now I need a new quantile because the degrees of freedom have changed. I need a new half width because my standard deviation, as well as the n and the quantile, have all changed. And so here's a way of if you've been doing this or even other programs for a while, you've encountered a situation where you're kind of stuck in a loop, and especially if you have a do while loop going on, it's all too easy to just get stuck in an infinite loop. So in order to sort of counteract that, what I'm doing here is I'm saying, okay, every 10th replication, I'm going to say, oh, here I am, and here's where I am about stuff. Okay. Now the while test, here's the subtle thing, and then this is more of a programming thing than anything else. I want to keep doing this. First of all, I want to make sure I have at least 30 observations. And so I'm going to keep doing it as long as my count is less than 30. And then after that, I want to keep going as long as my half width is bigger than my desired half width. This could be a greater than or equal to, greater than, equal to, doesn't matter. Okay, so again, to understand what I'm doing here, I have this, well, this was the other one, but I decided 2.5 was too big. I wanted it down to 2. So I'm going to keep doing replications until my half width reaches that level. So let's see what that looks like when we run it. Okay, so I'm saying my target half width is 2. And then every 10th replication, I'm just going to be reporting on how I'm doing. So after 10 replications, I was down to 5. And then it went down, then notice it went up. It doesn't always, especially for small values of n, it can go up and down, but after a while it has to keep going down. And actually the unless there's some kind of pathology going on, then it actually has to terminate at some point. The only pathology is if somehow our variance is infinite. And again, that normally doesn't happen. Okay, so we're getting down here. So notice, so here's at replication 100. Remember, I was around 2.6, and so, but that was too big. I wanted it down to 2. So here I keep going. So this is an alternative to, what could I have done instead? I could say, well, 100, let's try 110. Well, let's try 120 if it's not reaching it. If I just do this, I just set it off and then maybe wait, go have a cup of coffee, and I get an error about You're kidding me. Oh. How did that get in there? I could have sworn that was okay. So let's try that again. Okay, so again here, see now notice that here it's not quite so much of an issue, but I do want to make sure I have at least 30 replications. Why 30? I have no idea, but 30 is something that you can at least say, well, in the stats class, they said with 30 observations, the central limit theorem seems to kick in. So, so the 30 is something that you don't have to defend, but you can just sort of pass the buck. Say, it isn't me, it's my stats professor. And I can say that because I'm not your stats professor. And if you like your stats professor and don't want to blame him, you can blame your simulation instructor, so which is me. So he said that 30 is the kind of the minimum. But as you can see, 30, we need a whole lot more than 30. Again, the reason for this condition here is that sometimes, just by chance, you get a very small, your half width, just by chance, gets unrealistically small after just a few replications. It doesn't always happen, but okay, so here it took 182 replications, and we see that now notice that now our delay in Q, it claims to be like almost 37, but again, it's kind of a plus or minus 2. So that doesn't mean that what we said before when it was 35 something plus or minus 2 point something, these are overlapping confidence intervals. And so we're definitely in the right ballpark there. But again, if this 2 is still too big, then you could cut it down. And we can do the same thing with the time varying one. So here's the same model using the time varying. So again, now my desired half width is 2 customers instead of the 2.5 that I had before. I'm using the same truncation point and steady state time, the same truncating collection time, size time varying, the same outer stat, same simple stats, but then using the same, I better check my, okay, so again, I want an alpha of 0.01. My half width, I start with a number which is guaranteed to pass this, although it probably isn't totally necessary. Again, do exactly the same thing. Reset the inner stat, run the model, pass the inner stat mean to the outer stat, and now inside the loop, I compute my quantile, compute my half width, and here's my periodic reporting. And when I'm all done, I'm going to say that I had this many replications and report the steady state confidence interval. So again, now we're looking at the steady state average number in the queue. Okay, so going down and down and down. And the interesting thing is that this sequential method, it was originally developed by a statistician in the 1940s by the name of Wald. And it didn't have a lot of play in the statistics world, mostly because for a lot of the statisticians need to actually get real observations and not simulated ones. So, for example, some of you will probably do some kind of HSI, human systems integration, or human factors type of study for your thesis. And that will involve either giving people surveys, or maybe one popular thing is developing a kind of virtual environment training and then testing users on how effective it is. And the thing is that's for something like that, a sequential method like this is not going to be terribly practical. Why? Because you just don't have that many things. Here we're running for like 100,000, 110,000 time units, and we just don't have that kind of time. Or for the delays in queue, we were running for 110,000 delays in queue. You don't have time to run 110,000 experiments. But on the computer, we have lots of time. Again, this only took 40 seconds. And if you had a model that ran for an hour, again, you just start it up, you go and do something else, and you come back, and it's all there. So in this case, we were able to achieve our goal using only 129 replications in that case, but we were, again, pretty tight around about the same level. So the thing is that, going back to this, if we okay, so now why is this guaranteed to eventually work? I mean, it may take a while. Well, it all comes down to this expression for the half width. Let me write it again up here just to be a little bit more. Okay, so this is our half width. And let's look at what happens if, as the number of replications gets bigger and bigger. Well, as I said, the estimate of the variance, and in turn the standard deviation, is typically going to be very consistent, meaning that as we take more and more observations, this is going to get closer and closer to just some number, so to what the true standard deviation is. We don't know what it is, but the law of large numbers, or central limit theorem, is going to say that this is basically the law of large numbers said that this is going to get close to the actual one. This t quantile, if you remember, do you remember what happens to the t distribution as you get more and more degrees of freedom? This will actually converge to one other number, which is a so-called z value, that is the normal distribution. A t, as the number of degrees of freedom keep increasing, that will converge to just this number, and to get closer and closer to that number. So sigma and this z value, these are just sort of numbers. Those are kind of fixed. So what's the last thing? This n right here, and that's in the denominator. So as n gets bigger and bigger, so in other words, as n approaches infinity, this whole thing is going to, the half width is going to approach 0. I mean, in other words, as you take more and more samples, the half width is going to shrink to 0, which means eventually, for any given criterion that you have, it's eventually going to hit that. So in the case here, so let's say I didn't even want, like, let's say I wanted 1 instead of 2. Well, again, it may take a while. Again, infinity is kind of a long thing. But if I wanted, I had a half width of 1, then it will eventually get there. Now, the only while that's running, The only issue is that because it converges at the rate of 1 over the square root, that is actually relatively slow convergence. In other words, it's the convergence of this quantity, it will eventually get as small as I need to, but it's converging at a relatively slow rate. And it is going down, but as you know, as you, if we kind of start looking at the deltas here, so like 2.7, 2.5, 2.3, the deltas actually kind of decrease. So it kind of converges slower and slower, but it will eventually get there. And as you can see, we're, you know, it's chugging along. And again, if you look at the deltas are actually shrinking. And that's because as n gets bigger, 1 over the square, the difference between 1 over the square root of n and 1 over the square root of n plus 1 becomes smaller and smaller as n gets bigger. And we can see that happening here, but it will get there eventually. It has to, because mathematically, this has to happen. Because mathematically, it's, you know, we just have some constant divided by the square root of n, and as n gets bigger and bigger, it's going to get as small as we need to. Okay, so it's getting down there. It's getting down there. But again, as you can see, the deltas are getting smaller and smaller. And then finally, after, okay, before it took 40 seconds, now it took 2 minutes and 18 seconds. It took 433 replications, but again, notice that we are now plus or minus 1.